Welcome to this video on finding the moment of inertia for a continuous distribution of mass. We're eventually going to get to that point. What we want to look at first here is conceptually if we can predict what that will be. Now, what do we even mean by continuous distribution of mass? Well, in the last video, what we had was a very light, maybe aluminum rod, and we had two blobs of mass basically positioned at either end of that rod. And we were saying that the mass was located at a specific point, and it didn't matter how the mass was spread out. But now, if we took those two blobs of clay, which are the masses, and we spread them out over the length of the rod, maybe something like this, then would that change the moment of inertia? Well, hopefully you would say yes. Now remember, the first thing we have to remember is that moment of inertia is really describing resistance to rotation. So the resistance to rotate. But it's not just rotate in general, rotate at some point. So we have to define the axis of rotation. So over here, I'm just going to pick the center axis of rotation for now. And what we would say then is that each of these masses is located at a discrete position of L/2 away from the axis of rotation that I chose, which here happens to be the center of mass. So what we showed was to use the moment of inertia equation, which is just a summation of the amount of mass and its r or x or y or z position at somewhere from the axis of rotation. So in this example here, what I could do then is say if both of these masses are even, okay, or the same, I guess, we would say I is equal to m times L/2 squared plus the other m times L/2 squared. So what I'm doing here is just summing up all of the pieces. So I get m times L squared over 4 plus ml squared over 4, which is equal to 2m L squared over 4, which is just 1/2 ml squared. Okay, now what I'm going to do next is think about what is affecting the moment of inertia, the resistance. Well, if I have more mass, obviously that will make the resistance larger. Or if I have more mass located further away from where I'm rotating, that would also make it harder to rotate. So let's see if now if I move my axis of rotation to the end here now, what I would get for my moment of inertia is m times 0 squared, because this is located at the axis of rotation, so r is coming out to be 0, plus the m here times L squared, because it's all the way distance L from the axis of rotation, so that just adds up to ml squared. So you can see here that the moment of inertia doubled when the mass was further away from the axis of rotation. Now what we're going to look at in this case here is we're going to see is, does distributing the mass evenly throughout this whole rod make the moment of inertia larger or smaller? Well, if you think about what happened when we went from figuring out the moment of inertia from just one end to the center like this, we see that it got smaller when the mass was evenly distributed out and it was at closer positions to the axis of rotation. Now if you think about it, if I chop these balls up into lots of little tiny pieces and I spread the pieces all the way out over here, we see that we're actually going to have less mass on the edge than in this example, because the mass is going to be smoothly spread out throughout. So let's try to see what we'll do here if we're finding it about the center of mass. Well, I know that it's going to be less than 1/2 ml squared, because here, if all the mass is at the end, I have 1/2 ml squared, and now if I spread this mass out, I have less mass far away, so I should have a smaller value. Now what we're going to see here is that if I change this equation now to the sum of a tiny little piece of mass at a particular position r squared away from the center of mass, This R, I'm only working left to right here. So what I'm going to do is say that R, because remember R could be X, Y, or Z. And in my examples here, it's just going to be X. So I'm going to switch it to just being X. And what I'm going to say is that if I take each little delta M, each little piece of mass, and I locate it at some position X, and then I add it up to the next piece of mass at some other position X, so on and so forth, all the way across this rod, I would get some moment of inertia. And as I made each little piece of mass as close to zero as possible, then I'd be able to spread out the mass at more definitive or more infinite positions along the rod, and I could get better approximation. So remember, when delta M, small pieces of mass, goes to infinitely small pieces of mass, I start to use a differential form. And so essentially what's going to happen here is I'm going to find di, the tiny moment of inertia, for each tiny little dm of mass, r squared dm, right? And here I'm going to change my r squared to just x squared because I'm working just along the x dimension, but I could do it for all the dimensions. Now I know that when I add up all these tiny little pieces, right, that would give me the total moment of inertia over here, and this would give me integral r squared dm or x squared dm. So this is the integral definition of this equation that we had over here. Now, what we have to do is we have to think about the fact that the density might play into this moment of inertia where it didn't over here because we just had one point of mass blobbed at one specific space. So it wasn't really a concern. Here we're going to use linear density. And we are going to say that the density for right now, this density is uniform, meaning it's constant. There is no change. And so what I could say is that the total mass of the rod is equal to the density of the rod times the total length of the rod. For each tiny little piece, dm, of the object, right, all these little dm's make up the total m of the object, I'm going to be able to say that lambda is constant, and I'm going to change big L to just x. So I'm going to say every tiny little piece dx has a mass dm, and they all have the same value lambda. So what I'm going to do here is actually use that to change the variable of integration. So it's going to become integral x squared lambda dx instead of integral x squared dm. Okay, now at this point, what I can do is think about my axis of rotation. So I'm trying to do it about the center here. So that means that all these little pieces of mass that I'm going to be adding up at all these little positions, dx, all the way along here, are spread out between 0, the center, and negative L over 2, and 0 and L over 2. Okay, so my variables, or my limits of integration, are going to be negative L over 2 to L over 2. Now think about it this way. Because this is uniformly dense, what you could do is go from 0 to L over 2 or L over 2 to 0 and then just double that and you should get the same answer. So let's go ahead and do some integration here. So I'm going to pull lambda out because it's constant. Now if it were not constant, we could put its function in here as well and we'd be good. So I'm going to integrate this, which is integrating x squared, which is going to be x cubed over 3, and I'm going to evaluate that from negative L over 2 to L over 2. Alright, let's go ahead and do some substitution. So I have L over 2 cubed over 3 minus, and this is now negative, okay, so that will end up adding, so L over 2 cubed over 3. Okay, so let's now do our arithmetic. We have L cubed over 2 cubed, which is 8, times 3. Okay, that's this 3 at the bottom here, plus L, not 4, but L cubed over 8 times 3 again. And so that ends up becoming L cubed over 24 plus L cubed over 24, which ends up being 2L cubed over 24, which is 1/12 L cubed. Okay, now at this point what I want to do is I'm going to be able to go back to my original statement here and see that I need to include lambda. I left it out all the way through here. So lambda gets distributed all the way through this whole thing. And so I'm really left here with 1/12 lambda L cubed. Now I know that lambda is equal to m over L. And it's constant, so I'm going to go ahead and substitute that back into this equation. Let me make a little bit more room here. Okay, so at this point I have 1/12, and I have m over L, and I have L cubed, and so I factor out an L, and I'm left with 1/12 ml squared. So the moment of inertia for the rod about its center of mass is 1/12 ml squared. The moment of inertia, if all of the mass of the rod were located at just one end, is ml squared. If all the mass of the rod were located at each end, it's 1/2 ml squared. So you can see here that it is, in fact, a less moment of inertia than it was before. Let's end this one with looking at the moment of inertia about just one end now. So if we had this distribution of mass, but it wasn't about the center, it was about just one end. Well, if you think about it, is it going to be more or less than the other ones we found? Well, it's going to be more than this one, because now I have more mass further away from the center of rotation, or the axis of rotation, than I did in this example. So it's going to be more than 1/12, but it should be less than 1/2. So let's go ahead and do that. We don't have to do all of this work again, because the only thing we really need to do is change the limits of integration, because everything else is still the same expressions. So I really have here lambda times integral x. Let's do it at x squared dx. I guess we could go from there. And now we're going from 0 all the way to L. So this is going to become lambda times x cubed over 3, evaluated from 0 to L. And that's lambda times L cubed over 3 minus 0 cubed over 3, which is just all 0. So I have lambda L cubed over 3. Now remember, lambda was mass over length, so I'm going to go ahead and substitute that in. So m over L times L cubed over 3. Let's factor out an L again, and I'm left with, let's see, 1/3 ml squared. So that fits our prediction. We said it's going to be more than 1/12 ml squared. It's going to be more than when this happened, because more mass is located away from the center. But it's going to be less than 1/2 ml squared when that was happening. So yeah, it actually did work out. We ended up with what we expected. So in the next video, I'm going to take a look at some other common shapes for the moment of inertia, like a ring and a disc and those sorts of things, and like a hollow cylinder, and we'll get some more practice on applying the moment of inertia equation.